So I want to make a brief summary to this first integration approach. That this is the first work to demonstrate fully integrated volatile 3T and 4T NEM switches together with a non-volatile 17 NEM switch within the same foundry platform next to each other. And it is also the first work to propose a in-plane 4T silicon NEM switch using an analog dielectric plug. So why we want to use this 4T configuration instead of the 3T switch? Because the NEM switches is still considerably larger than the CMOS transistors. But the 4T configuration actually mitigates this gap in an interesting way. Not by shrinking the device size, but by shrinking the circuit size. So for example, if you want to build these demultiplex circuits, and if you build this with only the 3-terminal NEM device, we need 10 devices. But if you want to build this with the 4T NEM switch, we need only 2 devices. So what we lose in the device size, we win back from the device count. There is a cheating between the device level density to the circuit level efficiency. And this is a multiplex circuit that is implemented on this integration platform. So apart from the achievements, we also have some remaining challenges that we need to address before we continue our work. The first one is the low fabrication yield for the suspended 3-terminal NEM switch. Because of the long beam, the high length to width aspect ratio of the slender beams make them susceptible to the out-of-plane bending during the release edge. And second is the limited contact reliability and stiction failures induced by the switch contact design and also the contact material choice. And third is that this integration approach has a limited integration density because here you can see the switch is sitting inside the lens cavity and with the backend of the routing surrounding it. So it's a 2D planar integration method. And for the first challenge, we did a systematic investigation on the switch geometric parameters in the disease, and we mainly make the beam shorter, but we also need to modify the other parameters to compensate for the increased pulling voltage because we shorten the beams, right? And second, the contact reliability. We also do an extended investigation for the material that we use. We change it from gold to ruthenium. Because we know that ruthenium is hard and very resistant, and most of the commercial MEMS switches, they are using ruthenium combined with gold contact as the switch tip. So on this image, you can see that we also deposited the ruthenium contact through the window lift-off method with sputtering. And we know that it's an in-plane moving NEM switch, so the sidewall coverage will be very important. So we make a cross-section on the switch contact, and you can see there is very nice sidewall coverage for ruthenium on the switch tip. And we know that if we deposit around 40 nanometers of ruthenium on the top layer, then we get around 50%, roughly 20 nanometers, on the sidewalls. And with this ruthenium contact, we further investigated 3 different types of switch contact shape. First is the narrow contact, and then is the wide flat contact, and then we also have a round contact. And those are the environment results from the 3 different groups. So first, with the round contact, we see that they have consistently a larger pulling voltage, which is over 30 volts than the other 2 groups. And it also has a much higher hysteresis window. And for the other 2 groups, we see that they have a comparable pulling voltage level. But for the narrow contact switch, we see a much better endurance through extended cycling, and also the hysteresis window is much smaller than the other 2 groups. So we finally take this ruthenium-coated narrow contact design for our photo work. And for this third challenge for the integration density limited by the lens cavities, we developed this NEM-less 3D heterogeneous integration approach. So for this integration approach, we also have both foundry process and also the post-foundry process. And this foundry process is implemented by the XI10, which is the SOI-based process finished by X-Fab Germany. So first we have this integrated foundry wafer, which is built by depositing the back-end routings and dielectric layers on top of the SOI wafer. And at this foundry stage, the switch is not yet patterned, and also the silicon device layer is buried inside the back-end layers. So the next step of the first post-foundry process, we have to expose the silicon device layer and get access to that. How we do is first, we do the transfer bonding of the foundry wafer to a silicon substrate by either adhesive wafer bonding or direct wafer bonding. And I show here an example for the adhesive wafer bonding with a PCB layer. And this is done in the university clean room with a bonder and a vacuum. And the next post-foundry step, we do the dry etching to remove the silicon handle layer, and then we also selectively remove the underlying box layer to expose the silicon device layer. And next, we can do the in-beam patterning in the university clean room to pattern the NEM switches. In this way, if you look at the last image, the back-end layers are at the bottom of each of the switch terminals. So we call it a 3D heterogeneous integration. And also the NEM switches is patterned after the CMOS is finished, so it is a NEM last process. And in this way, this integration approach compared with monolithic integration can give us a much higher integration density through the vertical stacking of the back-end layers. So this is a 6-inch wafer after the bonding and removing the handle layer. And before we continue for the rest of the post-foundry process steps, we dice it into smaller chips, which is 2 by 2 centimeter. And for each of the 2 by 2 centimeter chip, we have a 4 by 4 array of different designs, which has 16 subchips. So on these designs, first we have the switches that is built by pure CMOS, and then we also have the NEM CMOS hybrid circuits. And most of the circuits are built by pure NEM switches. For example, we have this simple 3T40 cell, and we also have the logic gates and the memory cells. And finally, we also have a complete FPGA cell. So for the rest of the foundry process, this is done by on the 2 by 2 centimeter chips. And here we have a challenge that is different from the monolithic integration approach. The reason for this is instead of using the dense high-quality box layer as the sacrificial layer for the release edge, we are now etching the back-end dielectric. And they are less dense than the thermal oxide or the high-quality PECVD oxide. And they behave very differently during the buffered HF etching and the vapor HF etching. For example, this is the result after the buffered HF etching, and if you see the oxide layer in the switch gaps, it looks very nice and uniform. But if you do it with an extended vapor HF release, you see those pinholes created on the oxide layer. And especially when there is a reactive metal on the switch contact on the oxide layer, you see the phenomenon is much more severe. So why is that? That's because vapor phase HF, they can find every single gap between different layers and also the pinholes on the materials. So they will create a run-away effect along the metal and dielectric interface. Especially when we use some reactive metals like gold or even aluminum, this will become worse. So we finally divided the release step into 2 different steps. First, we use buffer HF to create a large undercut underneath the switch beams, and with only a small oxide pillar to hold the switch in place. And finally, we use the vapor HF to remove this pillar in a very short and low pressure controlled process. In this way, we can implement both 3T and 7T NEM switches on this 3D integration platform. And those are the switches that is with the interconnect routings and also the bond paths. And those are the released switches You can see the undercut around the switches, they look very nice and uniform, and the undercut after this is roughly 800 nanometers. So this integration approach can give us significant reduction in chip areas through this vertical back-end-of-line stacking. And also with the two-step release, we have a device yield more than 95% without collapsing the NEM switches. And also now we change the back-end-of-line metal from aluminum to tungsten, so we have a better thermal budget. After release, we characterize the NEM switch with a semi-automatic probe station equipped with a microscope, 4 SMUs, and the mirror switch with the dry air flowing through the chamber to remove the humidity in the environment. So first, we implement this 3T NEM switch with both silicon contact and also the ruthenium contact. So for the silicon contact NEM switch, similar to the other integration approach, we have very limited endurance. It only works for 2 volatile cycles before the extinction. And if you see the light blue line here is the second cycle, it has a much larger hysteresis window than the first cycle. And for the ruthenium contact switch, we see a different failure mode. So we didn't see the extinction failure during the extended cycling. What we see is the signal degradation. So this here I show 40 cycles, but the switch is switchable for more than hundreds of cycles. But after 40 cycles, what we see is that, so this blue line is for the first cycle, and you see the current can reach the current compliance we set as 1 nanoamp. But after 40 cycles, we see it's only 400 picoamp. So we see a largely increased contact resistance through repeated cycling. But until the end of the cycling, the switch is still mechanically movable. With this 3T NEM switch, we have built a large circuit with 12 switches in this integration platform. And also for the 17 NEM switch, we characterize both silicon contact, where it also only works for 2 cycles. And for the ruthenium contact 70 switch, we characterize it with 3 different current levels from 1 nanoamp to 100 nanoamp and to 1 microamp. And all of these groups, the switch can work for hundreds of cycles without extinction failure. What we see is the signal degradation. And only if we increase the current limit to 10 microamp, and then we see the extinction failure after only program the switch for 5 cycles. And the best result we get so far is that the switch can be activated for over 500 cycles before the degradation. So that's the second integration approach. I want to make a brief comparison between the 2 integration approaches. So for the monolithic integration, the NEM switch is patterned before the back end of line, so it's a NEM first process. And for the 3D integration, we have the switch patterned after the back end of line and wafer bonding, so it is a NEM last process. And the sacrificial layer for the monolithic integration is the dense high-quality box layer on the SOI wafer. And for the 3D integration, it is the porous and less dense back-end-of-line dielectric, which is deposited in the foundry platform. The wafer bonding is only required for the 3D integration approach, which slightly increases the complexity for the whole process, but it also gives us a much higher integration density through the vertical routings. And CMOS is compatible for both of the approaches, but CMOS is only implemented on the second platform.